Good afternoon, everybody, and welcome to this third lecture in the series of Active Planet. And I'm really very happy to be here for introducing the speaker of this afternoon. But before starting, I would like to introduce myself. I'm Miura Mandea. I'm working in CNES in France, and it was really my pleasure to put together these 4 invited lectures and this afternoon. As you know, our Earth is really a very complicated system. It's changing a lot in space and time. But the Earth, we are here, but we are also in another system which is much more complicated, and it's, of course, the solar system. And during this lecture, we were interested to see what's happened with the solid Earth, with the oceanography, with the atmosphere part, and also today with the solar system. So, Active Planet, why we are interested in? We are interested because, first of all, we are scientists, so we are very much interested to go on and to understand how our planet works and what's going around us. But not only, because I think it's also important for us to think about the society. We have also a role to play in our day society and to see everything around us from deep core to very, very far away in space. And of course, to do this, I show here the 4 invited talks. We already had 2, and today we have 3 and 4. And 3 is the winner, François Forget. So currently, François works in Institut Pierre-Simon Laplace, an institute of CNRS, in the lab of meteorology and dynamics. He's very much interested in planetary climate and atmospheres, and I think Mars, Pluto, but some extra solar planets are also on the table in his interest. Lots of projects, as you can see here, indicated. And he, of course, is in Paris today, and we are very happy to have him. But also he worked in NASA for a while, and I think he will continue to be involved in space. Even, as you can see, as hobbies, he really likes to go down diving. So, a little bit about what he's going to tell us, I hope, it's how to build something which could be a virtual planet, and this virtual planet has to behave as the real one, as us, our planet, so this is pretty complicated, I think, but also he's interested to use the terrestrial planets of our solar system to understand and to predict, if it's possible, how Earth is going to move, but also some exoplanets environments, what it is around, how they evolve, and what it will be maybe tomorrow. So I think it's all on my side, and now, François, the floor is yours, and enjoy, and I'm sure we will enjoy with you.
Thank you very much. Thank you very much for the invitation here at EGU. It's always a great time. It's always this meeting is more, every year is better organized. So I was invited to give a talk about activity everywhere. And so I first planned an 8-hour talk, and then I tried to design a story, in fact, a lot of small stories, and to tell stories about the solar system and a little bit of beyond to maybe in the room people who are actually Earth geophysicists who are not super specialists of solar system. So although I see a few faces that I know who knows everything about specific planets and other things. And I will try to convene and explain that lots of activity, lots of the action that is going on in the solar system and beyond is of interest for any member of the EGU, any participant of this meeting. Every people here could and should be interested in the science, the processes that we study on the other planets. And I will try to give you a few examples. So, to start with, I want to remind you that in the solar system, you have many, many words. Here is a kind of movie showing the different planets. We start with the big ones, but the reason is we also have all the moons of the giant planets, and we have all the asteroids and the trans-Neptunian objects, and all these are words. When you study them carefully, for instance, last year you had a mission around Ceres, which was just an asteroid. It's a complex word. Even if you go to the end of this list, it's only the bigger one. Some of these are extremely interesting. For instance, Enceladus here, I will come back to it, is a very interesting word. So, with all these words, it's interesting to see that a lot of the different scientific topics that are addressed within the context of the European Geoscience Union are actually used and studied during this meeting. So, of course, again, I could take hours to describe that. For instance, of course, if I start with the list, I look at atmospheric science of climate. This is my field. I could go on and on. The only thing I will say is just to remind you, indeed, we have plenty of atmosphere in the solar system. Of course, you have the 4 giant planet atmosphere, which are extremely complex. I'm interested, and it's actually a true challenge for atmospheric scientists. And in addition to that, you have animals which are closer to the Earth, the terrestrial planet atmosphere. Do you know how many terrestrial atmosphere we have? True atmosphere, you know, that we can study with the same equation as on Earth, with clouds and everything. How many? How many? In fact, we have 6 terrestrial atmosphere. The Earth, of course, Venus, Mars, Titan, Triton near Neptune, and Pluto. And all these atmospheres are really interesting, and they are true atmosphere, as I said, with the same equations and lots of processes that are similar than what you in some way find on the Earth. The good news is that we know a lot of data for very diverse sample of atmosphere. Some are very thick, some are very thin. All are interesting, and we have lots of information, more and more information, of course. If you just take Mars, of course, we have had a lot of missions. Right now, you have 5 orbiters, most of them studying, measuring in some way the atmosphere, 2 landers, just ongoing now. One is on its way, ExoMars, some died recently. If we go to Venus, Venus Express, I kept it on this plot because it's in some way still active. Of course, it stopped working a few months ago, but at this conference, there were lots of results presented. And here you have the Japanese Akatsuki mission, which is actually working around Venus. And you can see I can go on. On Titan, of course, you have the incredible Cassini mission still observing Titan. Triton was only observed in 1989 by Voyager 2, and another recent results, New Horizons flew by Pluto last summer, and provided us with a lot of information on the atmosphere, on this kind of new atmosphere. So this is my field. I could take hours. I won't actually tell much more about the atmosphere. Just to illustrate the newcomer, the Pluto atmosphere, which turns out to be beautiful and interesting. Beautiful because, as we can see with the high phase angle, if I use the technical word, you can see very well the organic hazes, and I use this picture to actually introduce the fact that it's a very interesting thing to note that a very important process in the other atmosphere, not really on the Earth, are actually the formation of photochemical hazes. On Pluto, you have the formation of photochemical hazes, which are actually organic hazes. They are quite complex. You can see all the layering here. The New Horizons team have some idea that they could be related to gravity waves and so on, but it's still a big mystery. So if you have any ideas to explain how you can layer it on the scale of several hundreds or thousands of kilometers around the planet with gravity wave or something, such a haze, it's interesting. So the point is that there are lots of action, lots of activity going on in other planets which are quite extraterrestrial, but many processes are common between the Earth and the other planet, and I will get back to that later. Okay, I could go on the list. For instance, if I look at more fundamental things, the geoscience, volcanology, seismology, what about the activity? So are all these planets dead? Very often, that's a question we get, is Mars dead, and so on. Of course, there are bodies that we all know are not dead at all. They are super active, much more active than the Earth. An example is Io around Jupiter because of its orbit, which is perturbed, and the gravitational forces from Jupiter. You have tidal forces that induce some heating and friction inside the planet, and you have a hyperactive geophysical cycle with constant, lots of volcanoes everywhere, almost constant eruptions. A nice picture from that is coming actually from the New Horizons spacecraft when it flew by Jupiter. It's the kind of movie, it's an 8-picture movie, showing you the eruption of this Vastar volcano near the North Pole of Io, and you can see, most of the time there is something going on like that on Io. So that's a superactive planet. But what about our sisters, like Mars? Is Mars still active today? Well, of course, when you look at the surface, you can see a lot of tectonic features, some volcanoes, and the good question is, you still have some geophysical activity. In fact, when you look at the topography map, again, you see, again, these volcanoes and these tectonic features, and the geophysicists can map and date the actual surface, the different lava flows coming from the volcano, and doing so, they found that typically, for instance, one of the most recent volcanoes, Olympus Mons, the caldera, seems to be quite old, okay, a few hundreds of million years. That's a result from Stephanie Werner and following Nocum. And it's only a few hundred of million years. It's 100 million years. It seems to be old, but it's only 2% of the age of the planet. So the first thing when you say, okay, you have lava flow that were formed a few tens of million years, that probably means that it will be surprising that everything stopped exactly before we arrive to look at it. So most likely there will be some more eruption in the future. But of course, we don't know when, and we may have to wait 5 million years to see a nice volcanic eruption on Mars. Meanwhile, to study, there are lots of project ideas, lots of studies. Mars is studied a lot. I could mention one project. Oh, I forgot that. This is a map, similar studies by Ernst Auber, which actually showed that there were a lot of lava flow, widespread lava flows, relatively recent in the Tarsis area. Okay. The project I was mentioning first is the ExoMars Trace Gas Orbiter. This is timely because the Trace Gas Orbiter, as you know, maybe was launched 1 month ago. It should arrive at Mars in October. And it is designed, we have several instruments, but a suite of instruments are designed to look for trace gas. This is where the name is coming from. And looking for trace gas, that includes gases like, I don't know, SO2 or other sulfuric gas and chlorine and possibly even methane, which is, and that could be the signature of a geophysical activity in the subsurface. And with such a mission, we should be able to quantify if there are still some vents and volcanic activity. Then, if you are interested in the geophysical activity on Mars, the next step will be this mission, InSight. InSight, if you're familiar with this design, is using the same spacecraft than Phoenix in 2008. And it will carry, it's a US spacecraft, JPL. It will carry a mostly European payload. And the prime instrument is this one here. That is, you can see the robotic arm will deploy on the surface. It's a seismometer. And the seismometer, it will be deployed very carefully. It will be covered with a kind of protection that you can see here, quite heavy to be sure the wind and nothing will perturb the measurements. The goal is to make super precise measurements, so precise that you need to have a perfect vacuum in the sphere containing the sensor. And that has been a problem, and this is why, due to the French development, the instrument could not be ready on time, and the mission had to be delayed by two years. Nevertheless, it will be a great mission because in addition to this seismometer, there will be some geodesy, some very precise measurements of the wobble and the motion of the planet that will give us some information about the interior and also in the atmosphere. And there will be this German probe, the MOLE HP3, which will dig into the subsurface to measure the heat flow. So this mission is really designed to look for the actual activity and maybe better understand the history of Mars. And this is really the first of its kind. Now, that was for Mars. What about Venus? Is Venus still active? Well, when you look at the surface, which was mapped by Magellan radar in the 90s, clearly you can see a lot of action, a lot of activity. There are lots of volcanoes, some are recent, but most of the action seems to have taken place several hundred of million years ago. Maybe 1 billion years ago, when there were what people think was a resurfacing of the surface. Oops. And of course, a good question is, do we still have volcanic activity? Do we still have volcanic eruptions? So there have been lots of studies, lots of papers. I could show two results. The first one is something that has been used to suggest that there were very present-day activity. In some way, using the same technique that what I mentioned for Mars, looking at trace gas. If you look at SO2, which is on the Earth, or maybe on Mars, and certainly on Venus, a signature of volcanic activity. Well, if you look at that on Venus, you see a lot of SO2. I don't know how much more on the Earth, maybe 1 million more than on the Earth and on Mars. But if you look at SO2, where it's easy to look at it, above 70 kilometers above the clouds, it was interesting in the 80s to see that there were the measurements show that there were a maximum here at the beginning of the Pioneer mission and then a decrease like that, suggesting that before that they were even putting a lot of SO2 in the atmosphere. And then, these are results from Emmanuel Marc, the SPICAV spectrometer measured again a rise like that and a decay. So suggesting, okay, there must be volcanic eruptions and so on. But you have to be careful when you look at this plot because you have to know that in the lower atmosphere, below the cloud, well below the cloud, near the surface, the SO2 abundance is supposed to be much higher than what you see here. So you have a kind of some SO2 molecules lying above a kind of ocean of SO2-rich atmosphere. So the key question is whether this is due to volcanic activity. Maybe not really the relief of SO2, but maybe some the result volcanic activity enhancing the transport of SO2 from the lower atmosphere to the upper atmosphere, or to actual, I don't know, long wave motion and transport in the atmosphere. So it's a key question. So looking at trace gas is not that easy to really constrain the activity on the volcanic activity on Venus. But there are other results. In particular, I want to advertise recent results by Venice Express camera. This paper in 2015, which showed looking at using 1.1 micron emission from the surface with the camera, the VMC camera on Venice Express. You could see that the surface is so hot that the emission you see is actually thermal emission. So you can actually indirectly measure temperature. And what could be seen is that there were, during a short period, on June 24, 2008, kind of extra emission suggesting that there was some hot lava there, and which disappeared a little bit later. If you look at the geophysical context, it makes sense. The geological context, it makes sense. There could be some lava some activity in Kaniki-Kasma. So there is a good story there suggesting that we actually, the camera was able, in spite of the very thick atmosphere and so on, to detect a lava flow, or whatever it is, a lake or an actual flow of lava there. So you can see I could go on and on. I mentioned I forgot even to mention plasma science and so on, because this community is very, very familiar to use different planets to explore their thing. Then, okay, geoscience, maybe I'll keep it for later, and I can go to cryospheric science. Cryospheric science. Do we have active glacier on other planets? Action on this field. And if you want to look for action with the water ice glacier, I will suggest first you go to Mars. Although it's not that easy, because on Mars today there is no permanent surface ice outside the polar regions. This is a map of Mars, old Viking mosaic, and you can see no surface ice. But if you look carefully, if you are a good geomorphologist, you realize that in some area, not everywhere, you have beautiful example of glacier, or at least signature of glacier. This is the remnant of moraines, clearly created by a flow of water ice. You have other moraines in this very interesting area of Deuteronomus Mansae. Other glacier, actually in the tropics, where it's supposed to be super warm, on the side of the volcanoes. And actually, Jim Head's team mapped this, all these yellow area. These are the big volcanoes in Tarsus area on Mars. And the yellow area here are actually full of glacier remnants. And at the time, it was enigmatic. But in the past 10 years, we have been able to understand how we could have glaciers forming where ice is even not stable at all today. We understood that it's because in the past million years, the Mars undergoes very strong Milankovitch cycle, if you want, strong variation of the obliquity and the orbital parameters. And it was easy with using global climate model, including water cycle, to show that if you really increase the obliquity, for instance, and you have ice cap, beyond a given obliquity, you tend to destabilize the polar reservoir where the ice is currently present. And the ice tends to accumulate. It does not tend to accumulate everywhere. We find that typically, for instance, if you use the version of a model of 10 years ago, the ice will tend to accumulate on the side of the big topography feature in the tropics, like the Tarsus volcano or Elysium volcano. This is a map of Mars. And it was striking to see that the area where the model would predict maximum accumulation, this is the accumulation of ice every year, is only 6 centimeters per year. But if you do that for 10,000 or 100,000 years, you have a glacier. And it was very nice at the time. It was a complete coincidence. In one given meeting, I showed these results, and Jim Head showed these results, and it works. So that's science at its best when it's very easy. Just change one number of your model, and you have a good match. And for this area, but also for the other area now, we have a good understanding that they are the results of climate change due to past glacial age, if you want. Now, these glaciers are kind of dead, and there's no more action. They are buried, they are rock glaciers, ice on the surface will not be stable, and as far as we understand, they're too cold to really flow. Maybe if you're a glaciologist and you want to work on action on Mars, maybe you can look at the North Pole. Here you have a beautiful water ice cap, which is 3 kilometers thick and maybe a diameter of 1,000 kilometers. The details are very interesting. You can see you have trough, which form a kind of with the form of spiral going around the pole, which has been enigmatic for many, many, many years. And we have been able to understand them when we got radar sounding. And radar sounding shows you that you have thousands of layers, so you could do a kind of stratigraphy, and just like is done in Antarctica, for instance, to look at the recent past of the planet. But this radar sounding also allowed us, and in particular Isaac Smith and Jim Holt, jackal to understand how the actual trough, you know, the spiral that you just seen, could form. It forms through a very complex process, not involving glacial flow, so there is no real glacial action, but it's a combination of wind, cadaveric wind, and transport and sublimation or condensation of water ice that slowly form the trough that you see here, and the trough actually move with time. And this was very well documented and modeled with different models and with the radar data. So, if you're a glaciologist and you say, I want active glaciers nowadays, what can you do? Well, good news. Since last summer, we have something for you. It's on Pluto. On Pluto, it was discovered that in a specific region, which is about 1,000 kilometers wide, on the opposite side compared to the moon Charon, you have an accumulation in a big crater of a very thick nitrogen ice in Lancis ice cap at the equator. We think we understand the origin of this. In fact, my student Tanguy Bertrand gave a talk about that yesterday, or Tuesday was it? And but what's interesting there is that you really have flowing glacier. They're not made of water ice. Actually, the mountains here are made of water ice, but they're at this temperature. It's like 40 Kelvin. The ice is solid like a rock, but the nitrogen ice is really flowing, and you see beautiful characteristic and signature of flowing nitrogen ice, which flow downward. There must be some accumulation process, sublimation process. We can model that. It's very, very interesting. Not only it's interesting, it's beautiful, because when you zoom on the side of this nitrogen ice, you see that just like on Earth, the water ice flow tends to erode and make very scarp mountains, which are very interesting. This is seen from above. You have also these beautiful images. You may have seen that were obtained at high phase angle, and you see the age of Sputnik Planum, so this area where you have the nitrogen ice cap, and these water ice mountains, which are 3,000 or 4,000 meters high, has been clearly sculpted or by some flow or turnover or what it is. So this looks very Earth-like, but it's more than that. It's more complex than that. It looks like Greenland, where you have what we call nunatak, and the water ice flow flowing and making cliffs. But it's more than that. And the reason is that if you look carefully, you realize that what I will call nunatak, the kind of mountains that seems to emerge from the nitrogen ice, seems to be clustered in some area around a polygonal shaped structure, which are about 10, 20 kilometers wide. And what is that? Another interpretation starts to be very extraterrestrial. The interpretation is that you have a thick nitrogen ice. This nitrogen ice induces some solid convection, slowly but efficiently. And the mountains that you see here are not mountains emerging from the earth. They're actually icebergs that are moved by the ice, and they're big. They can be 1,000 or 2,000 meters high, okay? But they are clustered like that on giant polygonal shape. And they're like iceberg. And the reason why it's believable is that water ice is less dense than nitrogen ice. So the actual mountains from the rock, on Pluto rock is ice, water ice, they can actually float on the nitrogen ice. So this is the paradise for a glaciologist, I think. Okay, I could go on. I forgot what is the next step. Oh, hydrological science, of course. I have plenty of story about that. If you are an hydrologist, where should you work? Where is the activity? Where is the action? Of course, the first step is on Mars. I said, as you know, that Mars today is a very arid planet with only water vapor, ice, and sublimation. But of course, if you look at the ancient terrain, you see where you go, where you have lots of craters, where you have had the surface which was formed a long time ago. Everywhere you look at terrains which are older than 3.5, 4 billion years ago, you see erosion due to flowing water, certainly, and hydrology. And of course, there have been a lot of hydrology, Earth-like hydrology studies, looking at the drainage density and stuff like that. It's been a big study to understand what was the rate of precipitation, the amount of water involved. So if you're an expert on that and you want to help the Martians, please join. And another example is also at the end of some rivers, in some craters, you have some deltas and basins. This is the first and most famous one in Es Belvarde. You can see the size here. And this is a beautiful delta, which was made by the accumulation of sediments transported by the water. And if you look carefully here, you can see a typical example of what you find on the Earth when you have meanders that close and you have accumulation of sediments, and exactly what happened here. So this tells us that it took some time to form this kind of thing. But the key question is how much time? So there are lots of work for hydrologists on Mars, because the duration of the liquid water period on Mars was the warm and wet Mars episodic or true for millions of years, or tens or hundreds of millions of years, is still an open question, in spite of many studies. Other studies include, of course, the studies from the surface that were done, that are notably done by Curiosity and the other rovers. For instance, Curiosity saw at the bottom of some small rivers, creeks, some pebbles that were clearly rounded by the flow of water, and you can compare that to fluvial conglomerates on the Earth. This is the Earth, this is Mars. You can see lots of sediments and stratigraphy and that were probably formed in presence of liquid water. And the other big information that came in the past 10 years is from the mineralogy on the surface, but a lot, of course, in space with Mars Express, Omega, the imaging spectrometer, and CRISM and MRO. And this is, for instance, a global map of clays, so phyllosilicate that are supposed to be formed as with the alteration of liquid water. And you don't find them everywhere. You only find them in very ancient terrain, as you can see here, and this map there. So there were some action, some activity for hydrologists, but this was a long time ago. So if you want present-day action, and you're an hydrologist, you have to go back to smaller things. And one famous feature that you can find on Mars are Martian gullies. This was discovered by Mars Global Surveyor, and there have been lots of papers on this kind of gullies since the year 2000. The first paper was by Malin and Edgett. And these are typical gullies you can find in many tropical mid-latitudes, southern hemisphere, mostly location on Mars. And they look small compared to the big rivers, but they are not that small. They are maybe 1 or even more kilometer long, and they are 10, 30, 20, 30 meters wide, with levees and alcoves and deltas, which are big. If you walk there, you will be impressed by the size. And for many, many years, we assumed they will be formed by liquid water. People say they could be related to the release of water due to aquifers. We worked on scenarios suggesting that they were also formed at high obliquity when, for a combination of thermal process and the water cycle could help liquid water to form. But suddenly we had to change our conclusions a few years ago when the high-rise camera on MRO showed that there are actually currently some gullies, at least channel, forming today. These are 2 images taken 3 years apart, and you can see that a big channel, it looks small there, but it's a big thing, formed during that time. Probably the same process that formed the entire thing. And we have many other examples now. That was a surprise. It was exciting. Maybe you have liquid water carving that. But when Colin Dundas and colleagues looked carefully, they found that, and I have another example that was found by my colleague Cédric Pillarget. People realized that the formation of these channels were not going on at a time when you have liquid water possibly forming, which was a surprise, but actually when you have CO2 ice on the surface. On Mars, the atmosphere made of CO2 condensed during fall, winter, and spring, and sublime. And when it sublimes, this is where the gullies were forming. And that was a a big surprise because it's then the temperature is around minus 135 Celsius. It's extremely cold. It's impossible to have any kind of liquid water. So the conclusion is a CO2 ice process must make these gullies, which absolutely look like debris flows and gullies that you find on the Earth in Iceland, in Greenland, and the Alps, whatever, near here. So what is the process going on? It's enigmatic because of course, you have CO2 ice that you can see here. This is what is white. But the CO2 ice that condenses in this location, this is the Russell crater mega dune. It's at 54 degrees Celsius. The thickness of the CO2 ice that forms is a few tens of centimeters, 20 centimeters. So just a kind of cover of ice which cover the bigger topography, and the dunes, the channels themselves are like 10 meters wide. So how can you make that? There have been some speculation. We proposed recently a theory based on some actual physical modeling with Cédric Pilorget. We published it in Nature Geosciences like December. What we did is to develop a full model of the thermal exchange that you have on such a surface. On the slope, you imagine you have the sand. Below that, you have frozen ice, water ice. We know that. Above that, you have the CO2 ice layer growing, and we account for all the processes of diffusion and all the thermal exchange in that. So when you do that, we did find, so you can see either the temperature profile, you have the depth below the surface, you have CO2 ice growing during fall, you have the ice cemented soil, it's very Martian. And what we find is that in spring, when the solar flux hit the CO2 ice, the photons, most of the photons actually go through the ice, hit below the CO2 ice, and they tend to induce sublimation below the CO2 ice. So you have an overpressure of CO2 ice. That makes two things. The first is that the CO2 will condense in the subsurface, in the pores, instead of the surface. So you have frozen atmosphere a few centimeters below the surface in the pores. The second is that you have a lot of overpressured gas that fill the pores there. And after a while, the pressure is so high that it moves the ice up, cracks it, and you have a kind of geysers. Actually, this was studied before on flat surface. And we found that the amount of gas that will then had to move from the subsurface outside through the surface grain was so high. We're talking about several cubic meters. And maybe locally, when you have the cracks where the gas goes out, it's probably tens of cubic meters for every square meter. Okay? So it's a lot of gas. We suggested that in spite of the fact that the CO2 ice cover is very thin, it's such a huge amount of gas that it could induce the instability of the rocks and the sand on the surface and create the debris flow and actually fluidize the flow. So the gullies, which really look like they have been created by a liquid, maybe they are created by a gas that fluidizes the debris. This exists on the Earth. It's not very common, of course. There is one case, one example, some dense, what is called dense pyroclastic flows, actually generated by outgassing during near volcanoes. And it was found that they have absolutely amazing properties. They destabilize the rocks on the slope of the volcano, and they can create gullies in some way, debris flow at least, that can go on very small slopes and so on. So that's just a model. One interesting aspect of this model is that it explains very well the distribution of gullies and the current present-day activity. We can really predict wherever the model predicts there should be some action. This is where the gullies are found, and especially nowadays. I won't detail that. But it's not hydrology. Thank you. So if you want, nevertheless, to do hydrology, you have to not use liquid water and switch to another liquid on the cloud, the planet, and a very good example. It's not a planet, it's a moon, it's Titan. And Titan is covered by clearly valley networks and dendritic valleys. This is the image taken by the Huygens probe during its descent in 2005, and you see this typical dendritic river, which were probably carved by methane, ethane, liquid hydrocarbon. And you have also, especially in the northern polar regions of Titan, beautiful, incredible lakes made of ethane, methane, whatever. Waves have been detected. There have been lots of projects to study them, and you can see clearly hydrology going on, but it's not water. In fact, we have, with my student Benjamin Charnet, we actually worked on a study where we tried to imagine what could happen on Titan when there were less methane in the system. This was motivated by the fact that the reason why there were methane right now is not really well understood. So it makes sense to assume that there have not been methane in the Titan atmosphere all the time. Maybe some time ago, it was mostly a nitrogen atmosphere, like it is today, with not much methane. And if you have not much methane in the Titan atmosphere, then you change the climate. It's colder, you form nitrogen ice clouds, and on the surface, you form liquid nitrogen lakes and rivers. So we speculated that maybe some of these could also have been carved by nitrogen, liquid nitrogen river some time ago. So if you are an hydrologist, you can also explore the possibility that liquid nitrogen can make rivers. In fact, this is now speculated for Pluto. Okay. You can see this long list. I'm almost done. Some people will say, okay, you can do hydrology, glacier, but you cannot do ocean. Well, as I showed, you have some pretty big lakes on Titan. We used to think they were oceans, but not anymore. But in fact, ocean in planetary science is a word which is becoming bigger and bigger. In fact, if you go on the JPL website, you can see that there are lots of, they make a big deal about ocean words. Ocean word program. This is supported by enthusiastic US Congress members, and they want to really have a big program to explore ocean worlds. And the motivation, of course, is the idea that on many planets, not only the Earth, you have ocean of liquid water, maybe suitable for life, but underground. So if I go through this infographic, this is Earth, of course. Ceres may have an ocean. Europa is the most famous one, and the objective of a major mission now at NASA. And here I stop, the list continues on and goes on. On all these planets, it is speculated or even proven that you have under the surface an ocean of liquid water. One of the most interesting places, as I mentioned before, is Enceladus, a very small moon of Saturn. It's small. It's smaller than, I think the diameter of Enceladus is smaller than the size of Austria. It's 500 kilometers. But yet, it was discovered years ago now that there were some eruption geysers of water vapor and many other species going on venting near the south pole of Enceladus. And if you have not followed that, you should know that recently it has been shown by two methods that the ocean, the sea that was speculated to be there, if you can read here, it's written that there should be at the south pole a pocket, a reservoir of water. We now believe it is a global ocean. So it's a global ocean which is deep, 30 to 40 kilometers deep, and buried below the ice, and which will be 10 kilometers thick. And it's interesting because this ocean is interacting with the silicate mantle, which is active. So you may have volcanoes and lots of things going on. So everyone is excited about that. And also on the Europa ocean. Okay, in the time that I still have, I will now switch to another subject. I've been listing all the action, the activity, and why, if you are a specialist of this or these processes on the Earth, you could or should be interested in some processes going on other planets. I'd like now to justify and explain why it is interesting to study other planets from the point of view of a geophysicist, a European geophysicist. So of course, the first reason why you explore the planet, let's be frank, is for fundamental research and exploration. We want to understand what's going on, the physics of the universe, somewhere understand origins, we look for life elsewhere, the possibility of life, and so on. But there is another reason, which is a little more useful. When I look at the program at EGU, I'm always stricken by, okay, the science we do on other planets is not very useful on everyday life compared to, you know, you have natural hazards and you have very climate change, lots of impacts, lots of science field here, which are very important for the future of humanity and for everyone. Studying Enceladus is not the urgency, but still, studying planets can be useful. And the reason is that we can better understand our planet Earth by studying other planets. Of course, that's what we call comparative climatology. And the spirit is that, just like in medicine, we study other animals to better understand the biology of humans. We can do that. So you'll see that I use this kind of metaphoric pictures to explain that, okay, by studying animals, other planets, we can better understand humans, the Earth. So there is a long list. If you try to imagine how is that useful, following Ralph Kahn, with whom I discussed some time ago, you can actually kind of rationalize that. It's nice to put together a list of why it's important, how you can really better understand the Earth by studying the other planet. The first thing is that you can general concept to place the attribute of a planet into a larger context. You can obtain data that are actually not available on the Earth. You can study effects which are subtle on the Earth but of much greater importance on other planets. So, because we need to understand the Earth very, very well. So if it's very subtle, it's difficult to study. Inspire new ideas, test tools, and concept. So I will show you a few examples of that. First, the idea is to general concept. To place the attributes of a planet into a larger context. And I think, without even thinking, now in geoscience, people are completely used to have generalized the concept of what they're using, volcano, atmospheric circulation features, in light of what we have learned on other planets. Even if you don't know anything about the planets, in your field, something is using other planets. So I could go on and on. My field is atmospheric science and dynamics, and of course, the Hadley cell, these waves, and so on. This has been studied on many planets and generalized. Another thing you can do is obtain data which are not available on the Earth. You have very different kind of story related to that. The big one, for instance, is just to understand what happened in the history of the solar system before a few million years ago. Because on the Earth, most of the archive are completely have been removed and eliminated. It's very difficult to go back to more than 1 billion years. You have a few samples in some locations, but if you know what is the story, it's much easier to go to another planet or on the moon, where you have lots of surface which have been there for billions of years. And that's how, for instance, we understood that 3.9 billion years ago, there were a heavy bombardment that completely changed the solar system, affected the Earth, because we realized that lots of the craters on the moon date from this period, 3.9, 3.8 billion years ago. We have no scenario to explain that, the NICE model and so on, and it's very important. That's for the big picture, but you can also obtain data on other planets just for technical reasons. One example is on Mars. Mars' atmosphere is made of CO2 at 95%. And unlike oxygen and nitrogen, CO2 has strong spectral signature, for instance, in the near-infrared. And, oops. Oh yeah, I have another story to tell, I forgot. Yeah, it's to say that not only we can look back at the light heavy bombardment 3.8 billion years ago, but this is also the time when life emerged. We have nothing left of this time on the Earth. 3.8 billion years ago, or 3.5, 4, we don't know, when life emerged, when something went from non-living to living. Maybe on Mars, where there were liquid water, we could find some remnants of this. I wanted to advertise the ExoMars 2018 rover. And also maybe later with the astronauts, you can see they look for fossil and molecules. So maybe this key science question, how life emerged, started, we will have the answer on Mars, or maybe other planets, on Moon. So another example of data that you cannot have on Earth, but on Mars, I was mentioning that, is, whoops, I don't know, there is a picture missing here. This is a CO2 absorption band, this is a spectrum, okay, with CO2 at 2 micron. And as I said, if you have a CO2 atmosphere, you have a spectral band, and you can actually remotely measure not only temperature, not only the amount of gas, but you can actually measure the surface pressure. And it's very difficult to do that on the Earth with a high precision. On Mars, you can do, and for instance, I give you an example of a paper we've done with Emmerich Spega some years ago. Using the Omega imaging spectrometer on Mars Express, we could map the surface pressure, and with a good treatment, we could retrieve the signature of long gravity waves, and we can learn a lot. And to do that on the Earth, it's super difficult. There have been some experiments like Pyrex in France and so on, where you put hundreds of barometers to study the signature of waves. On Mars, it's much easier, and we have plenty of data like that. So if you're interested, just ask. I expand another concept is the idea that you can study effects which are subtle on the Earth, but are much greater importance on other planets. Again, you have plenty of examples. On Venus, for instance, you have this huge greenhouse effect, obviously. But with one of the most famous examples historically in comparative planetology, it's often quoted, I don't know how much is true, but I think it's kind of true, is the chlorine chemistry. And what happened is that at the beginning of the Venus studies, it was assumed and realized that chlorine and all the chlor species were playing a key role, and there have been some lab experiments and so on. And these measurements contributed to reveal the catalytic destruction of ozone by chlorofluorocarbon, which led to the work by Molina, Roland, Sherwood, what's his name, Crutzen, and then the Nobel Prize. So this is very often quoted as a key example in planetary science, comparative planetology. Another example, which is more technical, a subtle effect on the Earth. It's not that subtle, but when you have convection on Mars, you have extremely strong convection during the day. The surface is heated by the sun, and the system is such, with the atmosphere is so thin that the convection is extremely intense, typically 10 times more intense than on the Earth. So by studying Mars, by modeling it, by measuring it, you can learn a lot about what is going on in a very intense, very unstable atmosphere with a strong, so this is just from what we call the large eddy simulation of daytime convection. And you can see all these ascending motion and so on. This was done with a model which was developed for the Earth. So it was nice to adapt them to Mars and test if they were able to do well. Similarly, when we did that for for Mars global climate model, we tested parameterization which are used in Earth's global climate model, and we could suggest a few improvements because it was so extreme. So I have plenty of movies, I won't detail them. Just to remind you that one signature of this intense convection, as you know, are the dust devils on most afternoon and many locations on Mars. You have these intense convections create vortices that lift dust because it's, again, 10 times more intense than on the Earth. Other planets can inspire new ideas. I also use a very old-fashioned traditional example. And one example was often quoted by Carl Sagan. Carl Sagan said, well, when we arrived on Mars in 1971 with Mariner 9, the climate was completely different because of a global dust storm. Oops. And so these are the global dust storm on Mars. And from this study, they realized that if you have lots of aerosol in the atmosphere, it really cooled the surface. They worked on it, and in the end, they produced the nuclear winter theory, which plays a key role in the negotiation to decrease the amount of nuclear weapon in the 70s. And this was directly inspired by Mars. It's Turco, Sagan, and all the other authors clearly say that. Finally, I have a few minutes left. Of course, you can test tools and concepts. I mentioned that we could test the models of convection, still not perfect, but more generally, we can test numerical climate models on the planet. And of course, this is important. We've been developing, I won't detail that, I will go fast, I have a few more slides, but I will skip many of them. Of course, we have been developing global climate models to predict the climate change on the Earth, and very often, climato-skeptics, for instance, will say, well, are you sure they work? Because if the climate is different, your assumptions are wrong, and so on. And what we do is we take the same model, which are based on numeric universal equations, and it's kind of true officially for Earth models, and we try to adapt them to other planets to really create virtual planets. So we do that for the Earth to predict climate change, and we do that for other planets. And it's a good question, does the model work? What we find is that, so there have been models for every terrestrial planets. We're now working on global climate models on giant planets, which is a tremendous challenge, but several teams are succeeding now. Oops. And what we have learned from this test is that by many measures, most of the time, frankly, the global climate models are very successful. You really adapt them, you change a few constant, gravity, the size of the planet, you put the right atmosphere, you move the planet, like to the Mars orbit or wherever, you let it rotate. It's only equations, and you get something which really look like the reality. So it's a good confirmation. An example I like to show is not Mars. Mars is very, in some way, easy. Is Titan. Titan, there have been, for a long time, our team and other teams have developed a global climate model. There is a nice story. It's, you know, the Huygens probe measured one profile in 2005. So this is a profile that was obtained around 10 a.m. local time, solar local time, and you can see the profile is subtle. You have some small changes. They look like noise, not very important. If you look at the adiabatic lapse rate that correspond to this profile, this is this plot. You see a little maximum here, another maximum here. It's not easy to use this thing. You have some structure there. Is that activity? Is that action? And in fact, some years ago, Sébastien Lebonnois and Benjamin Charnay did adapt, for some reason, use the new 3D dynamical core and so on, and just say, how do we compare? And what they find, okay, the comparison was not completely perfect, but what they find is that they had the 3 layers here. The lapse rate was really similar, and it could not be a coincidence. And the story is that, when you look at it, is that it's 10 a.m., okay, it's in the morning. This is the top of the boundary layer at 10 a.m. in the morning. This is the signature of the top of the middle layer the day before. And this structure here is the top of the convection layer during the previous season when the sun was at the zenith. So just with one model, it's very close to the Earth model, you could quite well understand the structure of the temperature without tuning anything. So it was a nice result. Okay, then, and there I will go fast. It's very interesting because we can also learn when there is a problem, when the GCM can fail, and there are many reasons why they can fail. The main one, of course, is when you have missing physical processes. Oops. That's a problem, of course, because if you miss, for instance, for many years, we used to neglect the relative effect of Martian clouds on Mars, because they're thin and they're almost negligible. But when we put them in, not only they improve the climate locally, where you have clouds, but they improve the climate everywhere. The baryonic wave, everything. So we missed a physical process, and I may have many of the examples. When you have an insufficient representation of physical process, I won't detail, but you can read if you want. When you have long time scale, that's very difficult sometimes. When you have long time scale and difficult show of initial states, good example are the giant planets. You need to have a realistic planet, you need to run for thousands of years. How do you do that? It's not easy. Pluto also is an extreme example because the relative time scale, for some reason, on Pluto are extremely long. So you need to run in theory, you should run your model for thousands of years, which is impossible. So we have tricks, but it's not that easy. A last example I will detail is weak forcing, when actually the evolution of the system really depends on a subtle balance between different processes that are not perfectly modeled, and then you're super sensitive. A good example is the Venus circulation. If you take Venus climate model, it's not too difficult to get a very good thermal structure. And you can actually force model with that. And what colleagues did a few years ago, and that's in a paper, in a chapter published by my colleague Sébastien Le Benoit from LMD, they did a comparison of the dynamical core, the dynamical solver that are used to compute the winds for in the Earth climate model. On the Earth, these different dynamical core in Earth-like conditions gives almost the same results. They are very reliable. Zonal winds and so on, they give the same thing. When you apply them to Venus, suddenly they disagree. This is a cross-section of the zonal wind for different kind of model, a spectral model, grid point model from different origin. And you can see for exactly the same forcing, the dynamics which is obtained is completely different. So since then, there have been some studies to understand that. But this was revealing. Again, the same plot made for the Earth conditions, you have the same zonal winds. So Venus was revealing, because it's difficult, the super rotation, the process that controls the circulation on Venus is a complex process. It's not easy to model. Okay, I'm done. Another lesson is that climate component can be applied without model change to most terrestrial planets. And this is important because now that we have tested, for instance, I gave you the example of the boundary layer scheme. I show you that on Titan, it will predict quite well the altitude of the boundary layer at 10 a.m., at noon, the season before, and so on. It seems that the boundary layer scheme, the turbulent theory that we use, works in very different conditions. It's not perfect, but it gives you some hope. So maybe same thing for the dynamical core, even though sometimes it's sensitive and so on. On this basis, we could say that we could maybe design a model which not only apply to these different planets, but even to every planet, both that you can imagine. That's what we have been trying to do, and the motivation has been, because there is a third motivation in the reason why we should study the geophysics of planets and the activity, is to general geoscience to all the planets, because there are countless examples around those stars. If some of you followed the talks by Michel Mayor, you have billions of possible very exotic cases. And it's a challenge for every field. We have to know if tectonic is very common or unique, plate tectonic, I mean, if the role of oceans on such planets, the atmosphere, the climate, the clouds, everything. So we need to generate the fundamental lessons that we have learned, for example, in the solar system, and to address these questions in light of the upcoming observations. How many planets may be suitable for life? Is the Earth exceptional? And the answer lies in studies that are done in this community. Okay, I think I'm done. Thank you.
For this tour in our solar system. It was really a very nice and fascinating talk. Thanks a lot for being with us today. And time for some questions and discussions. So, who is going to start with questions? Okay. One here.
François, you mentioned, okay.
I think you need the microphone. The people say it for the video.
So you mentioned that the Venus atmosphere is very difficult, really, to model. Well, on the other hand, the way it behaves, it really looks much more simple than Earth's atmosphere, Martian atmosphere. Could you please explain a little bit more why Venus atmosphere is so difficult for the numerical modeling?
Again, the fundamental reason I mentioned is that the Venus atmosphere actual circulation is the result of the combination of several processes which are big but subtle. Typically, the typical scenario that is told to explain the superrotation, you have experts in the room, is that you have heating in the tropics, transport of air toward the pole in the upper branch of the Hadley cell that transport angular momentum, that create jets, and then the angular momentum there is transported back to the equator by wave mean flow interaction due to typically barotropic waves, some baroclinic waves. So you have, if you understand what I'm saying, you have a kind of positive feedback that is stabilized by a subtle balance. That's my view. Positive feedback is that you transport air from the equator to the high latitude. So you have the conservation of angular momentum accelerate the wind. Then you have some waves that accelerate the wind there. And then this prograde. The atmosphere there is then still transported to the high latitude, so you have acceleration of the system, right? And you have the transport back and so on. So you have an acceleration that we observe in GCM, and that's a positive feedback. And when will that stabilize? The stabilization will depend on the exact conservation of angular momentum, the role of the wave, the way you resolve them. Some of the baroclinic waves that play a role in the transport are small scale. So what I showed was a pretty coarse scale model. I think with higher resolution model, we have better agreement. But you're very sensitive to resolution. What was even found is that you're sensitive to the initial state. So it is possible that you have, in the models, not in reality, but in the models, different initial state will give you different results. In addition to that, you clearly have a role played by thermal tides, other waves from below, and gravity waves. Gravity waves, which has to be parameterized, they are super small compared to the typical, and the source are not constrained very well. It's due to convection deep below, and they amplify, and they break, and so on. So this combination makes the superrotation difficult to model. And because, to summarize that, on the Earth, on Mars, especially on Mars, for instance, the circulation is really the product of the contrast between the summer hemisphere, we have heating, and winter hemisphere, which is cooling, and then you have direct forcing, and you have balance, and you have winds. On Venus, the actual heating is just a small, the temperature contrast due to the heating is a very small forcing. The entire system is balanced by a subtle wave mean flow interaction and so on. The forcing does not control much. So that's why it's difficult.
Okay. Any other questions? Okay. If not, I have a question. We are discussing in our days a lot about climate change, rapid climate change for our planet. And I'm wondering if you observe something like this on the others. Do you have periods where really climate change is really very, very fast? Which is you're thinking about?
So it's a good question. One aspect of the question is that some climato-skeptics have been very excited each time some climate change was mentioned on another planet, because some of them have been pushing the idea that the sun was inducing climate change. So for instance, when it has been noted that the red spot was declining, there were new red spots forming on Jupiter, that it was claimed that, for instance, the southern permanent polar cap of CO2 ice, I did not mention it today, which is at the south pole of Mars, is maybe disappearing. There was some speculation. That the albedo on Mars was changing. There was some speculation with the title Climate Change on Mars, published in Science. So, it always had a very strong echo in the climate-skeptic community, because they consider, and they still use it as an argument saying that it's the sun, which is climate changes the climate on the Earth, but on other planets as found by the observer. So that's one aspect. In all these cases, it's not true. Okay, the sun has nothing to do, and in most cases, there is no climate change. There is no change. It's just an evolution, which is a balance. So very often, it's not even an evolution, it's an evolution like that. So sometimes you have one measurement, the other measurement, you say, wow, climate change, and then you have like that. Like SO2 on Venus, for instance. It was true for the pressure, for everything. Now, do we have climate change on other planets? Yes. You have paleoclimates on every planet for two reasons. First, the as I mentioned, what we will call Milankovitch cycle, the change of orbital parameters and obliquity. That can be strong. It turns out that the Earth, as you know, has a very stable obliquity compared to many other, at least Mars and Pluto and so on. And the other reason is the change of atmospheric composition, the interaction with the surface, and it's probably true for Venus. There have been lots of work, what happened in the past 100 million years, but it's quite slow. Can we have faster climate change? I don't know. Climate change induced by volcanic eruption on Venus? Maybe, but it's an open question. So that was your question?
Exactly. Still lots of things. Yeah, to learn. Yes, another question here.
If somebody else wants, I can. Yeah. You mentioned Enceladus and the possibility for finding life there. Very recently, matter of a few past months, there was a model that suggested, model that took into account the dynamics and mechanics of the orbiting, that suggested that Enceladus was very recently formed, maybe members of...
Recently formed?
Yes.
Enceladus?
Yeah.
I don't know of any moon recently formed. I don't know about this paper. I don't know if Christophe Sautin or someone like is here now.
I actually don't know if it's. I think it's in review at the moment. So.
If it could be demonstrated, it will be amazing because nothing has formed recently in the solar system. Exactly. It will require an amazing coincidence to have an impact or something like that. It's almost impossible statistically. No, I would like to see the paper, even the draft paper, because maybe it's more about the surface or whatever, the processes, or maybe the ocean recently formed. You sure about your...
No,
anyway.
It's a person who deals with the physical models. So
if they can demonstrate it and convince the community, it's a credible result. But,
any other questions? Because this one you can discuss during the coffee break. No. So I think we have to thank